In class, we looked at a problem where a ball starts at the top of a hill with some initial velocity, rolls down the hill, slides across the plane, compresses a spring, and comes to rest, at least for an instant, at the end of the spring. We're given conditions on coefficients of kinetic and static friction on the plane and asked whether the object then moves from its position of at least temporary rest at the maximum compression of the spring. Now, people generally solve this problem by first analyzing the motion from here to here, then analyzing the motion from here to here. And that's natural because the problem did ask for the velocity at this point. So that was a perfectly valid thing to do. I want to make the point that we can solve the entire problem except for that velocity with one equation, okay, with one principle, with the principle of conservation of energy, where the work done by the non-conservative force on the system is equal to the sum of the changes in its potential and kinetic energy. I asked, and let me make one comment, some people tried to apply uniform acceleration to the motion of the ball down the hill because you were given this distance and this distance, so you assume a plane and so forth, but that's not valid, that's not appropriate. Actually, you probably end up with the same solution in this case, but you have a terrible misconception because there's no way to assume that the acceleration is uniform on this hill. The hill clearly has different slopes. So you really should never use the assumption of uniformly accelerated motion in a case where you don't have uniformly accelerated motion. It very often leads you to really bad results, errors, and it's very bad conceptually. Okay, so in that case we have this conservation of energy equation. The first question I posed was, which of these three quantities do you know? How can you most easily find? Most people told me the change in potential energy. Well, yeah, that is easy if the only change in potential energy is from here to here. You're given the height, you can very easily calculate the change in potential energy. However, you also have a change in potential energy before the end in the spring. And you don't know how far the spring compresses, so you can't find the change in potential energy. Similarly, work done by non-conservative force on the system, well, you know how far the object travels across this plane. Now, one thing we didn't do and we didn't discuss is it also travels across the plane as the spring is compressed. So you do have a little bit of an unknown there. If the only place the friction did work on the system would be between here and here, knowing this distance, and knowing the mass of the object, you know its weight. This is a horizontal plane. A normal force is perpendicular to that and equal and opposite to the weight. You could easily find the work done by the non-conservative force. Okay, so change in potential energy, again, that has gravitational and elastic components, so you can't do that. You could write the expression for this. You could use x, say, for the distance the spring compresses, and then you'd have an expression for the elastic potential energy, and that would be good. That could go into the equation. Change in kinetic energy, though, is really easy. You're given the initial velocity, and the final velocity, at least for this phase of the motion, is 0. So the change in kinetic energy is negative 1/2 mv0 squared, for v0 is the initial kinetic energy. Work done by non-conservative force on the system is mu k times the weight times delta s. Noting that the normal force has a magnitude equal to that of the weight, and no arrows over these, so these are simply magnitudes. If we put arrows over it, we'd have to have a negative sign on one side or the other, as I'm sure you understand. And of course the weight is mg, so it'd be mu k times mg times delta s. Now whether you let delta s equal to 100 meters, I think it is, that the object travels, or let delta s equal to 100 meters plus, say, x, if x is the distance the spring compresses, you're going to get a different result. one way as opposed to the other. We'll look at how that works out. Okay, so conceptually, we need an expression for this, we need an expression for this, we need an expression for this. This one has no unknown. This one has an unknown when you calculate the change of potential energy of the elastic potential energy change of the spring. And this one might well have an unknown, the same unknown, the distance the spring compresses is part of delta S. Okay? Now, another comment I made is you really need to use units. I gave you several reasons for that. Mainly, there are two really good reasons. One is if you use the units and do the unit calculations throughout, you're going to catch errors if you do the unit calculations honestly, rather than just slapping the units you think will occur at the end onto the final result. You do the unit calculations. You check and make sure that your equations are dimensionally consistent, that you have the same units for every term in the equation. And the other reason for using units is it keeps you thinking about the meanings of things instead of just plugging numbers into formulas and hoping it works out. You have no, if you use the units, you're going to tend to think more about the meanings of the quantities, and that's going to give you much better understanding of the physics and of what's going on in the situation. Another thing is, as an alternative to using units, you can do most of your solution symbolically using symbols without numbers, without units, and then in the final expression, plug your given information in, your known information into the equation with the units, do the unit calculations once, you don't have to write them down as many times, and interpreting your symbolic results gives you a much deeper understanding, and complemented with the use of units, you really get more of a depth of understanding. So, I'm going to proceed in the next video to write out the solution to this equation in symbols and plug in our known information to get a solution.